Hello everyone. So today we will be diving into several important concepts in the field of variational interference, generative models and their challenges. So over here we can see that in the variational interference we want to approximate the true posterior, which is often intraceable with a similar distribution q of z of x, and to measure how close our approximation is we use k-value divergence, which is defined as a expected log difference between the q and p. So over here we can see how it has been written, and if we use the Bayes theorem and rearranging with it, we will get this expression. And since this entire term is called as evidence lower bound, and after substituting it we will get the final expression like this. This means that the log evidence equals to the ELBO, like plus the KL divergence. Since KL divergence is always non-negative, ELBO is a lower bound of log P of x. And over here we can see that the KL divergence is a measure from information theory, like it tells us how one probability distribution differs from another. And specifically if we have two multivariate Gaussian distributions, so let's say P of x and Q of x with both mean and covariance, the KL divergence from P to Q is defined as this expression over here. And this formula has four terms, like one measures the difference between the volume via determinants and all, and the one handles the trace of the inverse of covariance product, and the other captures the square of the Mann-Hobelus distance between the means. The KL divergence is always non-negative and becomes zero only when the two distributions are identical. It is widely used in machine learning for a task like variational interface and model comparison. Yeah. And the KL divergence term in the ELBO serves as a regularizer in variational interfaces, specifically like VAEs. So the ELBO has been expressed as this, where Q of z is approximate posterior and P of z is prior posterior. So the KL divergence penalizes the differences between the approximate posterior and the prior term, which is the P of x, and this term ensures that the posterior difference distribution does not stray too far from preventing overfitting and maintaining the structured latent space. And like without this term, the model may overfit to the data, focusing too much on the reconstruction loss and maybe neglecting the latent space structure. And this also leads to issues like posterior collapses. Posterior collapses where the latent variable becomes ineffective or underfitting, and the model fails to learn any useful latent variables and becomes ineffective. So the mode collapse in GAN occurs when the generator produces a very limited variety of outputs, like which is often focusing on one or few modes of the real data distribution. And mathematically this happens when the generator focuses on the specific modes and the loss function. Some of the solutions include like min-batch discrimination, where this helps in detecting the correlations between the samples in a batch and forcing them to generate more variety of outputs. And this is one of the most WGAN, which is also known as Posterior GAN, and like we get smoother gradients when we use WGAN. And as we discussed, posterior collapse in the VAEs occurs when the model's posterior distribution of latent variables collapses to the prior distribution. So to address these issues, one of the common approaches is KL annealing, as it gradually increases the weight of the KL divergence term during the training, allowing the model to like focus on the learning and do the reconstructions as well. And other techniques like variational dropouts, which include sophisticatedly into the encoder to promote the diversity in the latent variable usages, and free bits. Together, like these methods help to ensure that the model learns meaningful latent representations and avoids posterior collapses and everything. So thank you so much for listening.